Hello again. Thank you for joining us today. Welcome to the Data Science Seminar from the University of Washington eScience Institute. Today, we will continue our mini-series of talks featuring projects from our winter Data Science Incubator program.
Hi, everyone. My name is Yiyu. I'm a second-year PhD student from Earth and Space Science, and I'm very to give this talk presenting my work on this open source object storage for distributed acoustic sensing data. During this winter incubator project, I'm working with eScience data scientists Naomi Altman and Rolf Vettel. So I study Earth structure using seismic signals, which includes earthquakes or non-transient ambient noise recorded by the seismic stations. These stations are usually manually stored around the Earth, mostly inland, but with very few underwater. Having a seismic station installed may cost a lot depending on where the station is. For example, UW has our own seismic network, and there are 5 UW stations installed in Mount Rainier. Each requires a lot of regular maintenance. In the North Seattle region, it could be easier to install stations, but there are still only like 25 stations installed, indicated by these blue triangulars. Please keep 25 stations in mind, since we will see later how a new method revolutionized the seismic observation. So when studied the near surface structure, the spatial resolution we could see using the seismic data is largely determined by how dense the stations are. So with the stations kilometers away from each other, usually it's not possible to have a sub-kilometer structure resolved. So to increase such spatial resolution, seismologists had using sensor arrays to have a dense resolution observation. For example, Lin et al. Shows a 6-month-long experiment in Long Beach, California region using more than 5,000 nodal seismometer seismic sensors. The average spacing between these stations are about 100 meters. Another example from Oklahoma by Doherty implement this lasso experiment in 2019, and it includes more than 1,800 sensors with 400 meters spacing on average. So those seismic dense arrays are usually formed by thousands seismic stations. The average spacing could be several hundred meters depending on the area of survey, and the battery within the sensors usually can support months of recording. But it still requires tremendous field work to deploy and retrieve the sensors back. In the meantime, the distributed acoustic sensing, or DAS, came. The DAS is a new seismic observation method that has recently allowed entirely new types of geophysical observation. Using a unit called DAS interrogator, DAS uses repeating laser pulse along the fiber optics and up to 100 kilometers to measure the phase change of backscattered light, which occurred due to the strain rate of the fiber. The figure here shows the recording of an earthquake from a single seismic station, 1D array with only time axis. But for DAS, it has 2 dimensions, still one time axis, but there is another, the channel index axis. This photo experiment near Sacramento, as an example, turns a 23 kilometers cable into 11,000 channels with 2 meter spacing. You could see the arrival from a magnitude 3.2 earthquake arrival through the entire cable. There are also strip-like signals, which corresponds to the cable segments near the I-5, and it turns out to be the car driving along the cable. So using these new techniques, it's possible to have a dense seismic observation system, and it's similar to the dense array in terms of the number of sensors, the channels, recording durations. However, the channel spacing is now at the order of several meters, which has been dramatically improved. And what is more important is that much less field work is required to conduct a DAS experiment. So let's take a look at some of the most recent DAS experiments. Each row here indicates a single experiment. We could see different configurations are used in terms of recording duration, sampling rate, channel spacing. But if we focus on the size of the data generated by DAS, this experiment usually generates tens to up to 1,600 gigabytes of data per day. That's a huge amount of data that could easily reach petabytes for a research group. So for Iris, it's like I'm not sure why it's happening here. I'm seeing like only, yeah, it's working. So Iris is like the National Data Center for Seismology. Researchers request data very frequently from Iris DMC. It's a huge data center. However, the amount of the DAS data generated by this experiment listed here has already reached the total amount of the seismic data archived by Iris since 1992. Iris is not providing any DAS data service at this moment. The huge data volume is one reason, but how DAS data are saved also hindered data sharing. So this motivated us to study if we can find a better way to archive and share DAS data. So how the DAS data are saved? The DAS interrogator usually saves data in HDF5 format. So it supports hierarchical structure. This is a breakdown of the structure of an example HDF5 DAS data. So here, the NT and N channel indicates the time sample and the number of channels for the experiment. So usually, this raw data set would take more than 98% space of the entire file. It's a 2D array of shape N channel times NT. So there are also sometimes some attributes that are attached to the data set which contains important metadata during the experiment. There are very small key value pairs and don't change much frequently during an experiment. The problem with these attributes is that we don't have a good convention for them. So we can leave that to the community to discuss for the metadata. Here I'm showing the previous slide. It's basically 1 minute of recording. So every minute, DAS interrogator will output a single file. These are the separate files, but if you append them along the time axis, it will form the continuous recording. So 1 minute of the data corresponds to a 2D array with length fs times 60 seconds, where fs is the sampling rate. 1 day of recording is then fs times 60 seconds times 60 minutes times 24 hours. If you're looking at the 1 month data, just multiply it by 31 days. So it's effectively a very wide matrix with fixed height. So then comes the problem. What if I want to analyze some signals longer than 1 minute? For example, the recording of an earthquake could easily extend across many minutes. So a common solution is to just open each 1 minute file, extract the data, and move on to the next. 1 minute's recording are then concatenated to get a longer one for processing. So let's go further than that. What if I only want the small segments of the data? For example, some cables here are above ground and may not have good data quality. It is possible to choose the 100 channel subarray, but just getting the data raws at once. However, all of these operations are based on the assumption that your data is locally saved, right? If a researcher does not have the raw data, it is required to make a full copy from the remote server to their local machine. Well, this is not good. Remember the typical data size of the data, the size of the DAS experiment listed in the several slides before. You may not have an interrogator or cables to run DAS experiment, but you would definitely need to buy a lot of storage to save this data. So what happened? What made this? The answer is inside of the HDF5 structure. We say H5 is self-describing, it has hierarchical structure, it supports data compression, it allows user-defined attributes, and theoretically, there's no upper limit of how big a single HDF5 file is. But all of these structure attributes, metadata, needs to be mapped into the linear disk space, and the data is then unevenly distributed in the file. And for H5, it used a pretty complex mechanism to track where these data are physically located in the files. So libraries will usually need to read several bytes or the headers to decode the structure and the address where the actual data is. But this process usually requires several reading operations, and it can get even more complex if data are compressed. The easiest way was still to access remote data. We still simply make a full copy, even if the data is stored on the cloud storage. So to help solve this problem, this is what we are proposing in this incubator project. The idea is simple. We convert H5 DAS data into some cloud-optimized data formats. We deploy Minnow as our local object storage. Combining these two, we create a platform that is able to provide data service in a much more efficient way. So first, we convert H5 into formats that are designed for cloud. So one candidate is ZAR, which chunks subarray as individual objects in the object storage. We designed the chunking schema in a way that for the common long-time series request, only a small proportion of the entire dataset is requested. This avoids accessing other unnecessary data, as highlighted here in this orange chunk. A similar format is TileDB, which use database to index the array. This format supports data compression, and it can save key value pair attributes and have a self-describing hierarchical structure, just like H5. But most importantly, they allow subarray request. The way we chunk the data is critically important for those two cloud-optimized formats. For example, if we chunk the DAS data along the time axis and try to get time series for 100 channels, we would need to access all data chunks with very, very low data efficiency. The data along the time axis are also usually numerically close to each other, which also affects the performance of the compressor we're using. For such reason, we want to design a schema for both ZAR and TileDB formats that gives the best I/O performance. So we use the DAS experiment from offshore Oregon, which turns a 95-kilometer ocean bottom cable into 47,000 channels with 2-meter spacing. The sampling rate is at 200 Hertz, which gives 1.2 gigabytes H5 file per minute. And we test the conversion of the data using different sets of chunking sizes and measure the time for the conversion in total number of objects we are generating in the object storage. We also test the reading performance by requesting 10 minutes of OI, the DAS data from our object storage from all 47,000 channels. We only request a 5,000 subarray from the shallow water segments. And we apply the detrending and pass filtering and extract some features from time series. And we track the time to finish the data querying and as well as the bytes received from the object storage. So the strategy for ZAR can be summarized as follows. So writing a large chunk for ZAR is fast, but since they are bigger, there could be more network overhead, especially someone is not requesting that much data. Having a small chunk gives you better reading performance, but it's slow to perform the conversion. And too many small objects would also slow down the object storage. One probably should optimize these parameters based on the data sets they have, the hardware they have, and most importantly, how the data are possibly being read. The strategy for TileDB is a little bit tricky. The arrays are all well indexed in the database, so there's almost no network overhead. However, the performance of the object storage is very important for TileDB, and it seemed to be a good idea only use used it on commercial cloud like AWS S3, where the hardware can support higher request rate. So the other key idea of our project is to use object storage. We are not in the cloud, but we could still deploy one locally using Minio. For example, here I'm uploading 1.6 terabytes of CDAS data, which also creates 1.8 million objects in the Minio. There are several advantages using Mini.io as local object storage, like it's open source, you can easily deploy it through Docker. As an object storage, it has good scalability. More importantly, it provides access control through the credential keys and secrets granted to user only with proper permissions. It also uses the same API as the AWS S3. The researchers could upload the data to the cloud, and their code would need very little modifications to work on the AWS. So to showcase our platform, we use another dataset from a dark fiber connecting UW Seattle and UW Boston campus. The cable goes directly into atmospheric and geophysical buildings in Seattle campus and is connected to a desk interrogator. The experiment lasted for 11 months, beginning April 2022, and about 2,100 channels are evenly distributed along a 10-kilometer segments. So the channel spacing is about like 4 to 5 meters spacing, sampling at 100 hertz. This gives 72 gigabytes of data per day, and the raw data is saved as a H5, a minute long H5 file. So we load one month of CDAS data into our local object storage as ZAR. We use 50 channel 1 minute data chunk, and we have this Python client to request data from our object storage server running at this URL and port 9000. We request the segments from channel index 500 to 1100. So it's a 600 channel subarray. We specify the start time and the end time, and the data is loaded directly into the memory. So here shows this 30 minutes data. You could see coherent non-seismic noise like this strip, and there are cars moving, and there are some data gaps for some unknown reasons. And we deployed a desk cross correlation workflow locally, but it's a very compute intensive, and would cost too long to finish. So we just put the data to the AWS cloud S3 bucket and run the computing on the AWS. The code we use on the cloud is still almost the same as we use locally. The correlation of 1 month's data is split into 100 smaller jobs and distributed over an auto-scaling group. So the group will automatically manage the types and number of EC2 instances based on the job requirement. And each small job will request 3 to 8 hours CDAS data from the S3 bucket, perform correlation, and write the hourly stacked cross correlation function back directly to another S3 bucket. So there are total 8 billion cross correlation being performed within 4 hours. And note that since we made no data copy to the instance, So the cost analysis for this cloud workflow is also pretty attractive. Hosting the data on the cloud costs like $1.3 per day on the AWS. The computing costs less than $15 using this spot instance. And for the cross correlation data product, it costs less than $1 to save. You can also download it to local for the analysis. So this workflow shows that our platform can make that data access in a more efficient way. It also shows the important role cloud computing can play in processing huge amount of data that generates. So these powerful tools accelerate the group getting this image of a virtual source gathered on the right-hand side. We will further analyze the dispersion of the surface wave and prop the subsurface structure underneath the cable. It also makes it possible to have a real-time shallow Earth monitoring on the cloud using this DAS data. So to summarize, we propose a data platform for DAS that deploy an object storage service with cloud-optimized data format. The cloud-optimized data format support bi-range data request and allows for distributed processing and efficient data retrieval. The platform uses the same API as AWS S3 bucket and allows access control, making data sharing, processing much easier, both locally and on the cloud. So this is here's the last slide of my talk. Thanks for your time. And you could follow this project on GitHub by scanning this QR code for using, or there's a link here. I'm not sure if time permits, but I'm also happy to go through short notebooks on the Google Colab, because I have the data server open to the internet at this moment, and we can query some of the DAS data, CDAS data from our platform, just for like a short tutorial. Thanks for your time. Yeah.
Thank you so much, Yiyu. We do have one question, and we can address the question, and then we could go and you could show us a demo for whoever wants to stay on and look at things. But let's just take the question now. Any thoughts on cable layout at trade-offs? For example, a single strand placed linearly versus an L shape versus a crossing or looping configuration like a figure 8.
Sorry, would you remind, like the figure,
Eight.
which figure?
Figure 8.
Figure 8?
Like a figure 8, like an 8.
Oh, okay. Yeah, so the cable layout is pretty important for the data processing. For example, for our desk, for the CDAS experiment, I'm showing a rough layout of the cable, because the exact, if there are any loops in the cable, or if the cables have some turning point, it still remain question, and there needs a really good calibration to mapping exactly the channels are located at. And the layout of the cable is also important for the cross, especially for the cross correlation, to extract because different layouts of the cable will have different sensitivity to either radio waves or love waves. Like for collinear segments of the cable, it will have the maximum sensitivity to the radio wave, while the perpendicular has the better sensitivity to love wave. So yeah, it's definitely important to address this. I'm not sure if I answered that question. So.
Yeah, I think you did. I think we can, for whoever is interested, we can move on and you can show us your notebooks.
Okay. So I can have this copy pasted in the chat session. Yeah, so for it's running. Okay. So for those who are interested, you can just click these notebooks. As well, it will lead you to a Colab notebook, and I have all scripts here. You can start installing some of the necessary packages. It might take like 1 minute to install. Oh, faster. So we can import the necessary client to the Python client to access the data. Here I'm creating this client instance with the bucket name, and the endpoint, which points to our object storage as a department. Anonymous data access is set at false, but in case that we want to publicize the data, we can set it to true, that anyone can access it without a credential. Yeah, it's okay. So I'm also creating this temporal access key and secret key for this eScience talk. So you can, yeah, there's a credential loaded at being saved as a credential file locally. If you don't have this credential, you can just there should be a input. You can just input it when running this function. Ooh, I'm not sure. Oh, okay. One moment. I'm having this runtime for too long. Yeah. Come on, Google. Yeah, for those who are familiar with AWS S3 bucket, S3 service, this bucket endpoint is a good clue that this is very similar to what AWS is using on their object storage. Okay. Okay, so it's telling me that there's no credentials, so I can just run this function, having the eScience as a key and a random password called eScience password. Yeah. Did I add anything wrong? Oh, I'm missing S. Okay. Okay, let me restart it from scratch. I'm running out of time, but yeah, it's just basically rejecting me because I'm giving the wrong password.
Again, I think that for whoever is interested, they can stay on and we can watch the demo. Otherwise, I'd like to thank our participants today, and we'll see you next time. We'll stay on until you finish.
Yeah, thanks. Okay. 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 All looks good. Okay, this should be good enough. Okay, so it's connecting to the client, to the server, and we have hosted some of the metadata here. It tells you where it's one of the experiment data conversion proposed by a global coordination, and it shows the start time and end time of this experiment. And the important one is this get data function that allows a subarray query. So where I'm getting 1 hours of that data for this channel 100. It's also to do this subarray query for channel 500 to 1100 for, I don't know, 45 minutes of data. Yeah, 45.
You have a question if you're running this on Colab GPU.
No, it is not using GPUs. GPU doesn't use GPU, so it's sending the data request to our server and send the data back through the HTTP. Yeah, so no GPU required. But if you want to perform more data analysis, like do the cross correlation, which I just show in the slides, it's definitely recommended to have powerful resources, but it's not required. Yeah, so that's the end of this tutorial. But yeah, okay.
All right. I think we will end here, and we will continue our mini series next time. Thank you so much.